Hello, I'm Jiyarpuram Madhusudan. I will be presenting the work package 2 of the 6G-DISAC project on use cases, KPIs, KVIs in the architecture for DISAC. So the outline of this talk will be starting with the basics of the work package, and then we will be presenting the results from this work package. Most of the partners in the project are also participants into WP2. There are 3 tasks. The first one on DISAC scenarios and use cases. The second one on metrics, KPIs, and the trade-offs. And lastly, the architecture for distributed sensing in ISAC. There are 4 deliverables in this project. The first and the third are the preliminary and final versions of the scenarios, use cases, and KPIs. And the other 2 are the preliminary and final versions of the distributed ISAC architecture. In terms of the interactions of WP2 with the other work packages, WP2 provides the high-level the architecture and the requirements, and in turn, WP3 gives us feedback on metrics. For WP4, similarly, we provide the high-level architecture and really high-level description of the protocol. The details of the protocol, however, done in WP4, and these protocol extensions are fed back into WP2. With WP5, which is involved with the evaluation, we provide the architecture and a couple of use cases, high-level use cases, from which WP5 will choose one for the demonstration. So for the achievements, for the task 1, we've defined the scenarios and use cases that benefit most from the DISAC framework. We've selected 2 use cases, one on the smart factory floor and the other on vulnerable road users. We will see that in more detail later on. For tasks, the task on the KPIs and KVIs, we have defined the relevant metrics and the KPIs and KVIs, and also study the trade-offs in the context of the DISAC framework. Again, we will see this more on this later. And finally, for the task 2.3, define the challenges for DISAC and the enablers that can help address these challenges. And finally, the architecture, which integrates all these enablers. Several presentations have been made to different industrial fora, to SNS projects, and also to standards bodies. Presentations present some of the sort of general concepts that we need to introduce before we go into the actual results of the project. So in terms of the scenarios and use cases, we are concerned with the partially automated driving systems here in the context of our use cases. And smart intersections, which are intersections which are well instrumented in terms of not just ISAC, but other devices such as cameras. Vulnerable road users are people on the roads who are like pedestrians, cyclists, and so on, who have to be protected as they're moving around the urban areas. AGVs in a factory floor are mobile robots, automated guided vehicles that are used for transportation and logistics on the factory floor. The foundations of the KPIs and KVIs. KPI is a quantifiable measure on whether a particular target we have fixed is achieved or not. So there's the conventional KPIs which focus on performance, but also composite KPIs that we have introduced in this project, such as efficiency and scalability, associating both of them, for instance. KVIs are KPIs, but at a more broader societal goals, like you can see on the figure on the right, things like sustainability, inclusiveness, and trustworthiness. Finally, semantic communications is a shift towards the meaning of the information that we want to provide, and not so much on the raw data itself. That helps us to do goal-oriented communication and sensing. So in terms of the architecture design, there were two main concepts that we've used. The first one is the separation of control from the data processing. So you can see that on the box on the left, blue on the top line, sensing management and control function, and the sensing processing function in orange. So the sensing processing function in turn is split into potentially three levels. One at the network level, which is local processing on the base station in UE, for instance, potentially at the edge, and also the central and the core network, and which enables us to support both distributed, hierarchical, and centralized architectures. So now coming to the result 2.1. There are many use cases defined in both the industrial fora and in standards bodies. So here the focus was on those use cases and scenarios that benefit from the DISAC framework. So we've chosen two in the context of this project based on the benefit, the DISAC benefit, where that can benefit from the distributed processing that's done in the project, business potential, and also the demonstration potential. That is where the proof of concepts based on the chosen use case can actually be demonstrated in the context of the project. So the two use cases are, the first one is on the smart factory floors. So this is for the guidance of the automated guided vehicles, both real-time mapping and localization in order to improve navigation, and the other aspect is to make sure that the safety between human and AGV, as both of them are moving around the factory, is well maintained. And we use the sub-6 GHz frequency for communications and the millimeter wave band. The other use case concerns the vulnerable road users at smart intersections. This uses multiple modalities such as cameras, radar, and so on, in addition to ISAC. And the goal is to provide real-time alerts to cars about the potential vulnerable road users at the intersection. WP5 has actually chosen a merged use case based on these two and some strong points of both. For instance, the multimodality, for instance, the mobility, and so on. So, and this is what has been chosen as a demo for WP5. In terms of the 2.2, for the metrics KPIs, the standards bodies again have defined for KPIs both communication and sensing KPIs such as data rate, and for sensing accuracy, resolution, and so on. The goal in the project was not to reinvent the wheel, so we focused on either additional measures such as ensuring continuity of service, energy efficiency, and so on, or, as I mentioned earlier, composite KPIs involving both communication and sensing. And we've also done a preliminary qualitative analysis of the gains that can be expected from DISAC. In terms of the key value indicators, you can see the figure on the right. This concerns things like sustainability, inclusiveness, trustworthiness, and which may in turn induce KPIs such as cost, coverage, and so on. So all of these have been studied in the context of this project. So in semantic communications, the KPIs, semantic communications is largely based on AI. So the KPIs are ones, and metrics are ones that we know from AI, such as precision, recall, the F1 score, and so on. We've also studied the spectral efficiency that semantic communication could bring. So the trade-offs are at two levels. One at the radio resource level in terms of the frequency, time-space division, in terms of slots available, and also the duplexing constraints for both FDD and TDD. The system-level trade-offs have to do with we have to meet both communication and sensing performance needs at the same time. So the trade-off that is achievable between the two. And then in terms of the KPIs, we've seen in an earlier slide that, for instance, the inclusiveness KPIs can be increased, but that will come potentially the cost at increased cost. So there is a balance to be had there as well. And finally, the balance between performance and computational complexity. Higher performance will involve higher complexity for both computation, and it will increase energy consumption. So finally, on the architecture part, as I mentioned earlier, we look first at the challenges. So starting from the right-hand column, um, sensing generates a large amount of data. So we have to find an efficient way to meet this using different data representations, some of which are highly compressed, compressed, and others which are less compressed, but provide higher performance gains. So we need multiple data processing in order to achieve the flexibility that's needed. The second one is to ensure continuity. The second challenge is to ensure the continuity of sensing service over a large area and over a large period of time. And this involves coordination between the different sensing nodes and the network core in order to ensure smooth handover. Finally, this need for support of heterogeneous devices, because the devices are quite diverse, and they can, in terms of both their computational capability, their energy capability, and their willingness to participate into sensing nodes. So this heterogeneity needs to be handled by the appropriate enabler. So semantic reasoning and control. So this helps us to meet both the parsimonious data representation, but also to achieve system level KPIs and KVIs in a much more efficient manner. So we'll see a little bit about all. So this gives an illustration. So starting from the top left from data representation, you can see right on the top, there's the quantized raw data, and then the more classic range angle Doppler maps that's used a lot in sensing. And then the point cloud. Point clouds are very compact representation, which involve for each detected target, the range, the speed, and the angle of the target. And at the bottom here, you'll see different AI-based representations. There are many possible representations. We don't have time to go into this in this talk, but you can see our deliverables for more details. Then moving to the bottom left, so there's the ensuring continuity of service of the sensing activity. So there's the target that moves across different sensing nodes, and the sensing nodes cooperate between themselves and with the network core to provide the smooth handover. So then moving to the top right, there's support for heterogeneous devices. This figure shows different examples of heterogeneous devices, for instance, low power sensors, high performance UEs, and RISC in order to extend coverage. Then finally, the bottom right, you have the sensing, reasoning, and control. The bottom blue part is the network layer, and the pink part is the semantic layer. So in the semantic layer, as I mentioned before, multimodality, we receive sensing information from multiple nodes, cameras, ISAC, radars, and so on. So we need a higher level representation, common representation, semantic representation of these data. And then, which enables us to do goal-oriented algorithms that adapt to the needs of the application based on where it is at the current stage of processing. This last slide provides an overview of the DISAC architecture at the network level. So starting from the middle part of the diagram where there's central SEPF and the SEMF in black. So the SEMF is the management and control function. It receives sensing requests from applications and then configures the different sensing nodes. The sensing nodes are here, the STX, SRX, like the base stations and the mobile nodes, with the appropriate sensing parameters, and then the sensing activity still starts. You can see from the STX, the green arrows going towards the sensing target in orange, and the echo signal being sent back to being received by the SRX, where processing may happen locally. That's the LSEPF, local processing, then potentially at the edge, and finally to the central SEPF, where the fusion takes place. So this is a quick overview of what happens at the network level. So thank you. I've made a quick overview of the work package 2 activity in 6G-DISAC. For more information, you can consult these links. Thank you very much.